Okay, so welcome back, and now I'm going to do the proof of the fundamental theorem of calculus part 2. And so what we're going to do is we're going to start by partitioning the interval from AB, right? And we're assuming that we have a continuous function, f of x, over the closed interval AB. And so we start by partitioning, or creating a regular partition of the interval AB. Okay, so we're also going to go the other way. So we're going to start with f of b minus f of a. So with all the things that are given, okay, we're going to start with f of b minus f of a. And we're going to see and show that this leads to the integral. Okay? So now, this is equal to what? Based on this, what is x sub 0? X sub 0 is a, and x sub n is b. So we can write this as f of x sub n minus f of x sub 0, right? Now, but we can also write this by expanding this out, and I'm going to start here. I'm going to write a little smaller, so we can write this as f of x sub n minus f of x sub n minus 1 plus f of x sub n minus 1 minus f of x sub n minus 2, right? And then I can continue in like fashion to f of x sub 1 minus f of x sub 0. Why? Because we just partitioned into n subintervals, and since this is continuous, right, over the interval, then we can write this difference equal to this. But then, as you can see, if we add up all of these intervals, we have the middle terms all start canceling out, and we just end up with this. So by expanding it out this way, we don't change anything. Okay? But we do it for a reason. So now what you're going to see is, now I'm going to write this as a summation. So I'm going to write this as the summation for I equals 1 to n of what? This is going to be of, f of x sub x sub I minus f of x sub I minus 1. Now, we know f is an antiderivative of f over AB. Okay? So f of x is an antiderivative of f over the closed interval AB. Okay? So then the mean value theorem says for I equals 0 to n, we can find a c sub I in each interval, or in each subinterval. Right? So, how do I say this? So, by the mean value theorem, there exists c sub I in the interval x sub I, x sub I minus 1, comma, x sub I, such that, what? Well, if I take f of x sub I minus f of x sub I minus 1, that's going to equal the derivative of f, right? So that's going to be f of x sub I minus f of x sub I minus 1 will equal f prime of c times, or c sub I rather, c sub I times x sub I minus x sub I minus 1. Okay, so that's by the mean value theorem, right? So remember, the mean value theorem says that there's got to be a number c in the interval such that the slope of the tangent line at that c value is equal to the slope of the secant line that connects the endpoints of the subinterval. So that's what this is saying. Okay? That's what that's saying. So now, what is that equal to though? Well, this is just delta x. So let's just write this as f prime of c sub I times delta x. And so now let's go ahead and take this and now plug it back into this formula. So now, let me erase this. So now what I'm going to get is hence f of b minus f of a is going to equal what? Well, it's going to equal this, but now each one of these is equal to this. Right? So I believe I could just write this as the summation as I equals 1 to n of f prime of c sub I delta x, just by substitution. And now guess what? Now we're going to take the limit of both sides. So there's no I in here, so if I take the limit of this side, it's not going to change anything. So by taking the limit of both sides, I get f of b minus f of a is equal to the limit as n approaches infinity of the summation of I equals 1 to n of f prime of c sub I delta x. And what happens to that limit? Well, this limit, what? Well, each c sub I value is going to approach x. So this just becomes, and this is a Riemann sum. So this is going to become the integral from a to b of f prime of x dx. Oh, hold on a second. Hold on. Did I mess up somewhere? No, this should be, I don't know how I did that. This should not be f derivative, this should be f. Okay, that's it. Have a great day.